Hello everyone, I'm Paul and today we're solving problem 1504, count submatrices with all ones. This is medium and this has at least two different solutions. And here I will show you both. Our job is here in the title. We are given a binary matrix such as this one, and we need to return the number of submatrices with all ones. Now, in case you know what a submatrix is, it can have two possible shapes. It can be a square or a rectangle. For example, here we have a valid square because it includes a 1. This is a valid rectangle. Remember, we always need to have all ones. For example, this is a valid submatrix, this is valid too, and for example, this is not valid because this shape is not a square and it's not a rectangle. Now let's say we are here, we are standing in this cell. From here we can't look in every direction because this is just not efficient. We need to find some strategy. And the strategy is the following. We will use this as our DP grid. Remember, DP is for dynamic programming. And here we will use each cell to store the count of submatrices in the current row which have the current cell as the right corner. Let's see what this means. For example, let's say we forget about these two rows and we are standing here. We can form one valid submatrix with this cell as the right corner. This is the only submatrix we can form, so we keep a 1 here. Now let's say we are here. Given that this value is a 1, we need to add 1 here. This is now 2. And what this means is this is a valid submatrix and this is also a valid submatrix. Next we are here, so we add these two here. This is now 3. And what this means is this is a valid submatrix, this is also a valid submatrix, and this is also a valid submatrix. So we are storing in each of these cells the number of valid submatrices in the same row which have each of these cells as the right corner. Now let's see the full approach. The result is initially 0 and we are starting from here, and given that this is 0 we continue. Now we are here and the only valid submatrix which have the current cell as the right corner is this one, so we keep a 1 here and we can add this to the result. So this is now 1. Next we have a 0, so we continue. Next we are here. This is a valid submatrix, and given that here we have a 0, the only valid submatrix in this row, in this cell, is this one. So we keep a 1 here and we add this to the result. Next we are here, so we continue. Next we are here, and given that this is 0, we keep a 1 here. So we add this to the result. This is now 3, and here's the interesting part. This is also a valid submatrix. So we are adding this value to the result also. So this is now 4. Now we continue in this row. We are here, and given that this is 1, here we have two valid submatrices in this row. This one and this one. So that's why we have a 2 here. So we add this to the result. This is now 6. And given that this is 0, this is not a valid submatrix, so we continue. Now we are here and this is a 1. So we are storing in this cell 1 plus 2, which is 3. And what this 3 represents is this is a valid submatrix, this is also a valid submatrix, and this is also a valid submatrix. So we add 3 to the result. This is now 9. And now we can check the upper row to check if we have more valid submatrices which have this value as the bottom right corner. And here we have a 1. What this means is this is also a valid submatrix. So we add this one to the result also. This is now 10. Now we are in this row. This is a 1, so we add 1 to the result. This is now 11. And given that this is 0, we continue. Now we are in this cell. First we are checking how many valid submatrices do we have in this row, and we have 1 plus 1. So we put the 2 here and we add 2 to the result. This is 13. And now we're checking if this is a valid submatrix. And it is, because we have a 1 here. So we need to add this to the result. This is now 14. And in case you didn't realize, when we are checking for the upper rows, we are always keeping the minimum value among these 2. We don't have 2 valid submatrices here, we only have 1. And from here we can also check if this is a valid submatrix. So given that this is 1, this is also valid. So we are adding the minimum value among these 3 to the result, meaning 1. So this is now 15. Now we are here. Remember, first we think in terms of rows and then in terms of columns. So first we do 2 plus 1, so we replace this with a 3. What this represents is this is a valid submatrix, this is also valid, and this is also valid. So we can add 3 to the result. This is now 18. And now this is the key for this problem. We are here and we are checking if we have valid submatrices with this row. Here we have a 2, so we know we need to take the minimum among 2 and 3 and put this in the result. So we know this is 20. But let's see what this means here. What this 2 represents is that this is a valid submatrix and this is also a valid submatrix. Because remember, this is the total number of submatrices in this row which have this cell as the right corner. So what this 2 means is that this is valid and this is valid. And what this means when we are here is if this is a valid submatrix, this has to be a valid submatrix also. That's why from here we are adding this to the result. Now we are here, so remember, first we think in terms of rows, then in terms of columns. So first we take the sum of 3 and 1, this is 4, so we replace this with 4. And what this represents is this is a valid submatrix, this is valid, and this is also valid. So we add 4 to the result. This is now 24, and now we can look at this row. And we are taking the minimum among 3 and 4, and it's 3, so we add this to the result. This is now 27. And what this represents when we are here is that this is a valid submatrix, this is also valid, and this is also valid. And now we can look at this row, and the minimum value among these 3 is 1. So we need to add 1 to the result. This is now 28. And what this 1 represents from this point is that this is a valid submatrix. So now we reach the end and we return the result, which is 28. Now let's analyze time complexity. We need to iterate this matrix, and we know this requires n times m. And also, when we are here, for example, we are checking for this row, and then we need to check for this row, and this requires times n complexity in the worst case. So n times n is n squared. So this is overall time complexity, and space complexity will be big O of 1. Now let's go with the code for this first approach, and remember, then I will show you a second approach that's more efficient. First we say n is the length of matrix, m is the length of matrix 0, and the result is 0. Now for I in range n, for j in range m, if the current cell matrix I j is a 1, meaning this is a valid submatrix, we need to update the value with the previous value in the same row. So matrix I j plus equal matrix I j minus 1. Now it might be a case that we are at index 0 when J is 0. So we need to say we add this if J is greater than 0, else 0. So at this point we can check rows. And first we say the current value is matrix I J. And for k in range, we are going in reverse here. We go from row I to -1 in steps of -1. Current will always be the minimum among current and matrix k J. And if at any point current is 0, we just break this loop. Now if current is not 0, we need to add to the result current. This is exactly the same we did in the drawing. And finally we can return result. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's efficient, but we can still improve this time complexity. We can go from n squared times m to n times m. So let's see the second approach. For this approach, we'll have the same input. The result is initially 0 and we have an empty stack. And more specifically, this is a monotonically increasing stack. You will see how this works in a few minutes. And we'll go row by row. So let's say we forget about this. We only have this row. This is a histogram which we will store in an array called heights, and this will represent the accumulated heights for every column if we take the current row as the base. So here you can see how this represents this row. So we start here, and given that this is 0, we don't add anything to the result, and we need to add this index to the stack. So here we have index 0, and we put a 0 here in the array counts. Here we are storing the result for every column in the current row. So the result for the first cell is 0. Next we have a 1, so we need to add a submatrix to the result. First, let's look here. This corresponds to our current 1. And this is monotonically increasing. Here we have index 0 in the stack, and height at index 0 is 0. And the current value for height is 1. And given that this is monotonically increasing, we can keep our stack as it is, and we can use a small formula here. We can take the result at counts and the last value in the stack counts at 0. This is 0. Plus the current index, meaning index 1, minus the last index in the monotonically increasing stack, meaning 0. And this is 1. So this one represents this submatrix. So now we can update counts at the current index with a 1, and we can add this to the result. So this is now 1. And we need to add the current index to the stack. So we add a 1 here. Now we are here and this is a 0. And this doesn't look to be monotonically increasing anymore. First we are increasing, then we are decreasing. So we need to remove elements from the stack. So first we look heights at index 1, meaning here, and this is greater than the current height, which is 0. So we pop this from the stack. Next we look heights at index 0, meaning this, and this is equal to the current stack. But we need this to be monotonically increasing. So given that these values are equal, we also pop this from the stack. So the count for this position will be 0, and we need to add index 2 in our stack. Next we are here. This is monotonically increasing. Heights at index 2 is 0, and the current height is 1. So we can take heights at index 2, meaning 0, plus the current height, meaning 1, times the current index 3 minus the last index in the stack 2. And this is 1 times 1, meaning 1. So the value in counts at this cell is 1, and now we can add 1 to the result. This is now 2. We add the current index in the stack. Now you have 2 and 3. And now we are looking at these two cells. So counts is empty again. The stack is empty again. The new histogram is this. Here you can see the visual representation of these two cells. For example, here we have 1 and 1. The sum of this is 2. That's why here we have a height of 2. And we do exactly the same here. First we have a 0. So the count for this will be 0, and we need to add this index to the stack. Now we are looking here, and we know this is monotonically increasing, so we keep the stack as it is. Height at index 0 is smaller than the current height. So now we take count at index 0, meaning 0, plus the current height 2 times the current index 1 minus the last index in the stack, which is 0. And 2 times 1 is 2. So the result for this cell is 2. We add 2 to the result. This is now 4. And we need to add the current index to the stack. So here we have a 1. And what these two represents is this is a valid sum matrix, and this is also a valid sum matrix. And now it gets interesting. We are here. We know the current height is 1. So this isn't monotonically increasing anymore, meaning we need to pop a value from the stack. Heights at index 1, meaning this, is greater than the current height. So we pop this from the stack. And now heights at index 0, meaning this, is smaller than the current height. So this is monotonically increasing again, meaning we can keep 0 in the stack. So now we do count at index 0, this is 0, plus the current height 1 times the current index 2 minus the last value in the stack 0. And this is 2. So we put 2 here in the result for this cell, and we add 2 to the result. This is now 6, and we need to add the current index in the stack. So here we have a 2 now. And what this represents is this is a valid sum matrix, and this is also a valid sum matrix. And this makes sense. What we are doing here in the histogram is we are taking this as a valid sum matrix and this as a valid sum matrix. We went from the current column to the last column in the stack, meaning from here to here. So we took this and we added this. That's what this 0 represents. Now we are here. The current height is 2. And height at index 2 is 1. Given that the current height is greater than the height for the last index in our stack, we are good to go. This is monotonically increasing, so we can keep our stack as it is. So now we take count at index 2, meaning 2, plus the current height 2 times the current index 3 minus the last value in the stack 2. And this is 4. So we put a 4 here and we add 4 here. This is now 10. And we add the current index here in the stack. We are at index 3. And what this part represents is this is a valid sum matrix and this is also a valid sum matrix. Here you can see this in the histogram. And what this part represents is this is also a valid sum matrix and this is also a valid sum matrix. We are adding the result for counts at 2, which is 2. Remember before we had this. So we are adding this valid submatrix and this valid submatrix. If we sum everything, we get 4. That's why we have 4 here. We add 4 to our result. Now we can continue. Now we are in this row. So this is the new histogram. Counts is initially empty and the stack is empty again. First we have a 1, so the count for the current cell is 1. We can add this to result. This is now 11. And we can add the current index in the stack, so here we have a 0. Now we are here. The current height is 3. We are here. And 3 is greater than heights at index 0. So this is monotonically increasing. So we keep the stack as it is. And now we can take count at the last index in the stack, meaning 1, plus the current height 3 times the current index 1 minus the last index in the stack 0. And this is 4. And what this part represents is this is a valid submatrix, this is also valid, and this is also valid. And what this part represents is this is also a valid submatrix. So basically we are adding this, and this. So the result for this cell is 4. We can add 4 here, this is 15, and we add the current index to the stack, now we have a 1 here. Now we are here and this doesn't look monotonically increasing anymore. So we need to pop something from the stack. And we check heights at index 1, meaning this, and this is 3. 3 is greater than the current height, so we pop this from the stack. Now we check heights at index 0, meaning this, and this is smaller than the current height. So now this looks monotonically increasing, meaning we can keep index 0 here. So now we take count at index 0, meaning 1 plus the current height 2 times the current index 2 minus the last index in the stack 0. And this is 2 times 2 is 4 plus 1 is 5. And what this 4 represents is this is a valid submatrix, this is also valid, this is also valid, and this is also valid. Remember, the current cell is always the bottom right corner. And what this 1 represents is this is also valid. So we put this 5 as the result for this cell. We add the 5 here, this is now 20. And we add the current index in the stack. So now we are here. First we need to check if this is still monotonically increasing. The current height is 3. It's this. And heights at index 2 is this. So this is monotonically increasing. This means we keep the stack as it is. So we take counts at the last index in the stack, meaning 5, plus the current height 3 times the current index 3 minus the last index in the stack 2. And this is 1 times 3 plus 5, 8. What this part represents is this is a valid submatrix, this is also valid, and this is also valid. And what this represents is this is valid, this is also valid. Here we have 3, 4, and 5 valid submatrices. That's how we get 8. So we put 8 here, we add 8 to our result, this is 28. We add the current index to the stack, this is 3. And here we reach the end, so we can return the result, which is 28. So with this approach, time complexity is big O of n times m, and space complexity is big O of m. I know this can be complex at first, but I recommend you to take this step by step. So now let's go with the code and hopefully you will get the idea. First, n is the length of matrix, m is the length of matrix at index 0, the result is 0, and height is initially an array with 0 times m. Now we can say for I in range n, we are iterating rows here. First we have an empty stack, this is an empty array. Count will be an array with 0 times m, m is the length of each row. And now we can iterate every cell in each row. So for j in range m, and first we say if matrix at ij is 0, we reset height at j back to 0. Else we add to height j a 1. So now we can say while we have a stack and the height at the last index in the stack, meaning stack -1, is greater or equal to height at the current column, we pop the corresponding index from the stack, so stack.pop. This removes the last index. And why are we doing this? Because we are building a monotonically increasing stack. So after doing this, if we still have a stack, we take the last valid index and we'll call this previous. This is stack at -1, and count at the current column, count at j, is count at the previous valid index plus the current height times j minus previous. Else, meaning if we don't have a stack, this means we can take every value from the first column to the current column for the current row. So count j is height j times j plus 1. We are doing times j plus 1 because we are taking every value from column 0 to the current column. And after doing this, we can add to the stack the current column, we add j, and we add to the result count j, meaning the result for the current cell. And finally, we can return a result. So this is it for the code. Now let's submit this and see if it works. This is height, so let's fix this and try again. As you can see, this works and it's more efficient than the previous approach. I know this can be quite tricky, so I recommend you to try to visualize this approach. If you didn't get the idea, maybe you can try to watch this video again, especially the part for the second approach. And if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.